Anyone involved in machinery has surely heard the saying, big factories freeze, small factories heat, roadside shops bang away. What does this saying actually mean? Let me explain briefly. In the machinery industry, there's a golden duo, the shaft and the bearing. Anywhere there's rotation, these are used. So let me ask you, how are these two assembled together? You'd surely say it depends on the size, and there are three scenarios. One is a large hole fitting over a small shaft. One way is fitting a small hole over a large shaft. And then there's the case where the diameters of the shaft and the hole are exactly equal. Oh, well said. But even Uncle Wang at the village entrance knows that, strictly speaking, in the field of mechanics there is no concept of equality, and dimensions are not a specific value. Instead, it's a range. Everything involves tolerances. So a more professional way to say it is if the hole is larger than the shaft, meaning the lower tolerance limit of the hole diameter is greater than the upper tolerance limit of the shaft diameter, then this connection is no problem at all. It's smooth as silk and slides right in. Plus, once connected, there's still a gap. So this type of connection is called a clearance fit. It is precisely because there is a gap that the connection becomes loose and slack after being joined, unable to transmit large torque. Going further, if the lower tolerance limit of the hole diameter is less than the upper tolerance limit of the shaft diameter, but greater than the lower limit, well, this can get confusing, so be careful with your CPU. In simple terms, it means the tolerances of both overlap, which makes the relationship between the hole and the shaft interesting. The hole diameter might be slightly larger or slightly smaller than the shaft diameter. If it's a bit smaller, then the connection won't be as smooth. You'll need some force, like hammering or using a hydraulic press. This type of connection is called a transition fit. Compared to clearance fits, it is more difficult to disassemble, but the positioning accuracy is higher, and the transmitted torque can also be slightly larger. Taking it a step further, if the upper tolerance limit of the hole diameter is smaller than the lower tolerance limit of the shaft diameter, it truly achieves what most people understand as a small hole fitting over a large shaft. The technical term for this is an interference fit. An interference fit is very sturdy, but the problem is, how do you fit it together? This brings us back to that saying at the beginning. Big factories freeze, small factories heat, roadside shops bang away. Oh, it's not easy. We've come full circle to address the topic. If you've got some spare cash, you can buy a bucket of liquid nitrogen, submerge the shaft, and cool it down. Cooling causes it to contract, and once it shrinks to be thinner than the hole, it can be fitted. If your budget is average, you can buy a furnace, put the bearing in it, and heat it up. Heating causes it to expand, and once it expands to be thicker than the shaft, it can be fitted. If you're dirt poor and even a furnace is too expensive, then you'll have to rely on brute force. Borrow a big iron hammer from a neighbor and pound it in with all your might. Interference fit seems rough, but it's simple and reliable, capable of transmitting ultra-high speeds and ultra-large torque. Therefore, in the industrial world, interference fit is likely the most common connection method between shafts and bearings. If you take apart any car on the roadside, you'll find the connection between the hub and the bearing is an interference fit. If you go to your hangar and disassemble a plane engine, you'll find the compressor disc, turbine disc, and the large central shaft also use an interference fit. If you really want to know what the downsides of an interference fit are, I think the most direct issue is the difficulty in disassembly. Whether you freeze, burn, or smash once it's on, taking it off won't be easy. It could be connected for a lifetime. At a glance, an interference fit relies on the friction between contact surfaces. We learned in middle school that friction is the result of pressure. So where does that pressure come from? Essentially, it's due to the elastic deformation of materials. The inner components are compressed, experiencing elastic contraction. The outer components are stretched, experiencing elastic expansion. Even Uncle Wang from the village knows this. After elastic deformation, materials tend to revert to their original state. This force of wanting to revert to the original state tightly presses the inner and outer components together. Pressure multiplied by the friction coefficient results in enormous frictional force. You'll struggle to pull it apart. But Uncle Wang also knows that on the basis of elastic deformation, if force continues to be applied, the material might undergo plastic deformation, which is irreversible, permanent deformation. Once it reaches this stage, the material is essentially ruined. So you have to be careful. Everything needs moderation, exercise restraint, and definitely don't overdo it. For an interference fit, if the interference is too large, excessive pressure can occur on the fitting surface, leading to plastic deformation. So you ask, how can you ensure enough pressure during design while preventing plastic deformation? If the parts and conditions are relatively simple, experienced formulas and manuals can handle it. Many industries have traditional formulas passed down orally or written on paper. But when things get a bit more complex, experience alone won't be enough. In the 21st century, finite element analysis has become the mainstream method. For example, the well-known structural analysis software AI-FEM can perform interference fit analysis. The software includes built-in examples of rotor interference fits. By following the tutorial, you can learn quite a bit. Welcome mechanical enthusiasts to download from the official Tianfu software website. The software comes with a free trial upon installation, and the interface is cleaner, more pleasant than ANSYS, Mechanical, and ABAX. It also features an AI smart assistant. For questions about finite elements and software use, asking AI is much more convenient than browsing forums for tutorials. Alright, that's it for this video. Enjoy using the software, everyone.